Okay, we're going to continue on here. Chapter 15, new starting. There you go. All right, so earlier this morning in fine lectures we did earlier, we talked about one of the two sort of K values we're going to talk about in this chapter, which is again KSP is what we focused on. Again, KSP stands for the solubility product. And as we talked about, again, it is essentially the equilibrium constant for things that are insoluble based on solubility rules. And the main things that we talked about again is typically these equilibriums are written solid on the left, aqueous ions on the right. And as we kind of went through it, we could use KSP to do several different things. We could use the KSP value and we could figure out the molar solubility of something, which again is moles per liter, or we could also figure out the grams per liter solubility of a compound. We can, if we know the solubility of the compound, we could actually figure out what the KSP value would be for that particular compound by doing a calculation like that. We also talked about several things that affect solubility. And again, the major things that we talked about was, again, common ion. And as we talked about with common ion, again, that's going to cause a shift to the left there. And that's going to really decrease the solubility of that particular compound if you do have that common ion present. We also talked about pH, especially when we have insoluble bases or acids. And in general, we can use the pH to either kind of in some cases improve the solubility or not improve the solubility or decrease the solubility of a compound. And lastly, we talked about, kind of the importance of concentration as well. So the concentration of those ions that are floating around in the solution and you want to make some type of precipitate is really important because if the concentration of those ions aren't enough or proper enough, even though again solubility rules may tell you you should see a solid, you may actually not see that solid form because you just don't really have the right concentrations of everybody and everybody's too dilute. Other aspects that we saw at the very end with that example, we could definitely do things very easily in terms of selective precipitation by using KSP. We could use the KSP values, our sort of expression, to figure out if we have a precipitating reagent, which is something we're going to add to a solution to precipitate out something. We could figure out the concentration that's needed to do that. We could also liken that problem if we have multiple things floating around that solution, but only want to take one out and kind of leave the other one in there. We could really judge our precipitating reagent and get the right concentration dialed in that we could just simply take one out of solution and leave the other one still floating around. Any questions on any of that stuff that we talked about earlier? All right. So now the second part of chapter 15 here is the other type of equilibrium that we're going to talk about. And this involves complex ions. And a couple of things about a complex ion is a complex ion is typically a metal ion. And a lot of times it's a metal ion, like a transition metal that has a fairly good positive charge, like a +2, +3 sort of positive charge. And it is surrounded by one or more molecules or ions. And these sort of molecules and ions that surround the metal are what are referred to as ligands. And ligands are Lewis bases. If you remember from the last chapter, a Lewis base is something that will donate a pair of electrons. So again, this is the Lewis definition of an acid and a base. And if you think about a metal ion that is positively charged, that's in the middle, that's going to act really as a Lewis acid, which is an electron pair acceptor. Because as you know, if you become positively charged, you have lost electrons, which means you're electron deficient, which makes you a really good Lewis acid because you'll be happy to pick up some electrons because you obviously have spots for them. So you could think of a complex ion almost as a Lewis acid base type of situation that's occurring. And we have these ligands that are attaching. And if we look at this, in this case, we have cobalt 2, which is our metal. We have chloride here, which is our ligands in this case. And it makes this complex ion on this side, which is our COCl4 2 minus. We saw a little bit of complex ions when we were doing the pH and hydrolysis sort of experiment where you had like the copper kind of ion, and I'm like, throw out some waters on it, right? And, that's essentially a complex ion as well. Water is a very good ligand. Chloride, by the way, is also a very good ligand because, frankly, it is negatively charged, which means it has electrons to give. Water is polar, has those non-bonding electrons there on the oxygen that can be donated. So water is a very good ligand as well. Now, because this sets up an equilibrium in solution, we get our favorite thing ever, which is another equilibrium constant to add to our giant growing list of K values. This is known as the Kf value, or the formation constant. And the Kf, or the formation constant, is the equilibrium constant for complex ion formation. And it is basically just like any other equilibrium constant. We're going to go products over reactants, and will give us our Kf expression. As the value of Kf increases, so does the stability of the complex ion. And that's just the basic equilibrium idea. If we have a large value of K, that means we mainly should have products. And in these reactions on your product side, you have your complex ion. So if you have a big Kf value, you will actually make a complex ion is pretty going to be favored pretty good. And you're going to have a lot more products, which is where your complex ion is essentially there. Now, one of the things about how these ligands come onto the metal is they're kind of like how hydrogens are released from an acid. Hydrogens come off an acid basically one at a time. These ligands add to the metal also in a stepwise fashion, one at a time. So what we're actually looking at here is the overall reaction for that process of the complex ion being formed. What actually happens, as I mentioned, is it's a stepwise fashion. So really the first thing that would happen here is our cobalt would just pick up one chloride, and it would make COCl plus. And by the way, that is an equilibrium, and you could have an equilibrium constant value for just that little step there. The next thing that would happen is that COCl plus would pick up another chloride and make COCl2. And you also could have an equilibrium, thank you, constant for that step as well. Then continuing on, we're going to pop on our third one here. And we'll get COCl3 minus. Also could have an equilibrium constant. And lastly, after we put on three of them, we will pop on the fourth one there. And we'll make COCl4 2 minus in this case. Also can have an equilibrium. So this is the step-by-step sort of process that gets us to this overall reaction up here, where it just kind of shows, hey, we toss four of them on there. And again, they don't all four just kind of pop on there at once. They are added in an individual step. We obviously could get to that overall reaction by taking each of these equilibrium reactions and adding them together. And if you do that, that cancels, that cancels, that cancels, and you're left with the overall reaction, which is a cobalt hooks up with 1, 2, 3, and 4 chlorides to make this complex ion right about here. This would have a Kf value for it, which, by the way, if we knew the values for each of these steps, how would I get it? What do I do with all those numbers? I multiply them. So remember, when you're adding equilibrium guys together, the K values get multiplied. So you would multiply all those values together to get there. Yeah. Any questions on that there? So once again, ligands added one at a time. Um, a lot of times you may be given just the overall sort of ending reaction for it. Sometimes you may actually be given just the individual kind of steps and not the overall reaction. So sometimes you may have to add up all the individual steps to get the overall reaction to sort of do the calculation. And sometimes you're just kind of given the overall reaction. So it is a variable type of situation sometimes occurs in these problems. All right. So as I mentioned before, what makes something a really good ligand is things that are negative because again they have gained electrons, so they have electrons to donate, which makes them a Lewis base, and really polar things that have some non-bonding electrons, some lone pairs, also make really well. So as we saw there with water, chloride, ammonia, also a fairly good Lewis base, a really good Lewis base actually. And it is polar and it's got those non-bonding electrons that it can donate as a Lewis base. Sometimes when we do look at a complex ion, sometimes we're interested in what is known as the coordination number. And the coordination number is how many atoms are directly attached to the metal in the middle of the complex ion. So for example, if we look at this guy here, we basically have a cobalt hanging out there in the middle. And then we basically have 6 waters attached to it. By the way, the water would attach through the oxygen because the oxygen has those electrons, is also more negative, and the metal is positive, right? So attraction, opposites attract. And we would go like this. That's 4. I might be able to squeeze it in. Maybe I didn't do too bad here. Like my H's are going the wrong way now. All right, we'll go that way. I think I got them all in there, maybe. And this is basically complex ion. By the way, this overall thing has a +2 charge, and that +2 charge is coming from the cobalt because each water is neutral, right? So water doesn't have a charge. So the overall complex ion there is. So when we talk about the coordination number, when we look at really what's happening here is we have this atom, this atom, this atom, this atom, this atom, and this atom. Those are the 6 atoms that are directly attached to the cobalt in the middle through the oxygen, and it would have a coordination number known as 6. Now, if we did the cobalt there with the chloride, we would basically have this deal. And once again, we have 1, 2, 3, and 4. The overall charge here is -2 because this guy is +2 and each of the chlorides is -1. So -4 and +2 leaves you a -2 overall charge, right, on our complex ion. This would have a coordination number of 4 in this case because there's 4 chlorides attached directly to it. Now, the thing that sometimes people will think at this point is, well, isn't just the coordination number like this little number here on the bottom that tells you how many of those ligands are attached? And the answer is not always. In this case, in all these ligands that we see sort of displayed right here, these ligands, and we'll talk more about it in a later chapter, but these ligands are what are referred to as being monodentate. And monodentate, mono meaning one, means that they will attach to the metal through one atom only. So when they attach, even though water's got 3 atoms, it will always attach through the oxygen, and that's what's referred to as being monodentate. It will attach basically in one spot. Now, as we will learn again a little bit more in a later chapter when we kind of go into a little bit more detail on it, there are ligands that have the ability to attach in more than one place per molecule. So, for example, if we had, oh, let's steal some of the page here to do it. If we had, say, a formula like do something like CO E2O42 or -2. So let's say we had something like this here. Now, if I were to ask you what the coordination number is, you may be tempted to tell me, well, probably it's two because it says two right there. But the difference here is the ligand in this case is C2O4, which by the way is C2O42 minus. That's oxalate. And if you draw oxalate, oxalate looks a little like this if you draw it up. Chemistry like can all go. And oxalate is two carbons and four oxygens, where we have two single bonded oxygens and actually two double bonded oxygens. And the way that oxalate would attach, for example, to the cobalt that would be in the middle of the complex ion is if I drew it again here, I won't put all the dots in this time. It is going to attach via both of the single bonded oxygens here because they have really all those nice lone pairs and it's really the polar side of the molecule there. Which means if I have two of those oxalate molecules, it will also attach there, right? Which means really in this particular case, there are how many atoms directly attached to that metal? It is one, two, three, and four. And this would actually have a coordination number of four. And that's because oxalate is what is referred to as being bidentate. It can basically attach in two places per molecule. So you get a 2-for-1 discount on that deal, right? So for every one molecule, you get two attachment points, and that gives you kind of a double in the coordination numbers. So there are other ones that could attach in three places per molecule. There's something known as EDTA, which if you've ever looked at any labels on certain things, you'll actually see that sometimes written in there, EDTA. It could attach in six places per molecule. So it's really good at surrounding metals. And as we'll talk about in later chapters, right, they're sometimes referred to as metal chelators because you put something like that and it's just going to grab up the metal basically and surround it because it's going to bind in multiple places to it. So coordination number is not necessarily how many ligands you have attached to it, and it does depend on the type of ligand you have. It's how many atoms are directly attached to the metal in the complex ion. Questions on that there? So let's take a look at this problem here and we'll go through it here together. So we could talk about some of the different things that we do definitely in this type of calculation that we don't do, say in a KSP calculation or previous calculations as well. So in this particular one, we're going to take 0.2 moles of copper 2 sulfate. We're going to mix it with 1.2 molar ammonia. And we want to know what is the free copper 2 concentration at equilibrium. So once again, this is not always the case, but for this particular problem here, we're just going to keep everybody's concentration, like everybody's volume to 1 liter. So we're just going to assume everybody's going to have 1 liter as their volume, just to keep it simple. Other times you may have volumes given to you. You got to take them into account. But here we're just going to make sure everybody just ends up at 1 liter. So we can look at our equilibrium here, and this is really the overall sort of formation of our complex ion. Again, here the ammonia is our ligand, right? This is our obviously metal that's going to be in the middle of our complex ion. And since there's four NH3s added, like we talked about before, they actually will come on one at a time. So what we're looking at here is the overall reaction after all four of those have been added. So with that, we have the overall Kf value here of 5 times 10 to the 13. Like normal, we could do a equilibrium expression, which is our Kf. It would be our complex ion here, divided by our copper concentration and our ammonia concentration. And like normal, we also still need to, again, take it to the fourth power. And that's going to equal what we got down on the bottom there, 5 times 10 to the 13. All right, so in this case, we want the concentration really here of everybody once it's mixed together, and since everybody's going to keep basically 1 liter as our total volume, we will have zero point 0.2 molar of copper 2. This is going to be our source of copper 2 ions that are going to be floating around in the solution. And for our ammonia, once again, since we're going to kind of keep everything at a total volume of 1 liter, we will have 1.2 molar of ammonia floating around, and we'll have 0 of this guy. All right, so the first thing that's different in this type of problem than in what we have done previously in most cases is this. When we look at the K value here for our KF, is that a small value or a large value? That is a large value, right? Very different than the super small values that we saw there with our KSPs, right? So typically KSP values, as we saw earlier, are typically very small equilibrium constant values. KF values are typically very big, like sometimes to the 23rd or 40 type, really, really big values. Now, because that's a really big value of K, we actually make an assumption in this case when we do these type of problems. And the assumption is we assume that because we have a big K value, that all of the metal gets used up. So here we're going to assume that all of the metal is going to get used up here. And because the K value is big, that means we should really have pretty much products at equilibrium. And because it's fairly good size K value there, we should have pretty much mainly products. So the assumption is, even though this is a reversible reaction because of the value of the K here, we're almost going to think of this as a one-way street type of reaction. Everybody's going off to the product side, and everybody's going to end up, especially the metal, is going to pretty much 100% end up in the complex ion because of that K value. So what that means is how we sort of approach this ice table is we actually know the change because of our assumption that all the metal should end up in the complex ion. The change that's going to occur here is actually the metal's concentration will be our change. So normally we have done up to this point kind of use a number in the change part when we did moles. Here in KF1s, we typically also use a number for the change part, not X's or anything like that. We actually just use the number. If we were to sort of use X's like we normally would have done, right? Our change would look something like this, right? We would go minus X, we would go minus 4X, right? And then we would go basically plus X on the other side. But since we actually know what the change is based on our assumption here, we actually can just, instead of using X, use the number. So our actual change part here would be minus 0.2 minus 4 times 0.2 and plus 0.2. So again, it's the same idea as how we would have done it with our X's. But once again, since we really know what the X value is going to be in this case, we use the number. We still have to, as you see there, we still have to obviously take the coefficient into account and all that like normal. So that's going to get us down here to our equilibrium line. And we're going to end up with 0 of our copper 2. We're going to end up with 1.2 minus 4 times 0.2. We're going to end up with 0.4 here. And we're going to end up with 0.2 here, right? So remember that the question here is actually asking how much of the free copper 2 we would have at equilibrium. And at equilibrium, we could see that we would have 0, which means this wouldn't be much of a problem if every answer was 0, right? So clearly it's not going to be 0 as the answer, right? Otherwise, we wouldn't have to do anything. So we do make this first assumption that pretty much all the metals should end up in that complex ion. But in reality, this reaction is not a one-way street, right? It is actually a reversible reaction, which means the second part of the assumption is this, that even though we assume almost 100% of it should go to the product side, because this is still a reversible reaction, there should be a smidge of it heading back in the other direction. And the amount of free metal that should be there in the end should be a really, really small number. Yeah, because pretty much all of it's really over there on the product side. But because it has to go in both directions and it is reversible, you will just have this little smidge of it that's going to break apart and kind of stay apart and not be part of the complex ion. So what we do in this case is, although we kind of zeroed out the metal in this case, at this point, we now go back and go, okay, I'm just going to kind of call the metal X, and I'm going to try to figure out what is the actual copper's concentration. I could do that very easily by using my Kf expression, because now I have some equilibrium concentrations of people that are in my Kf expression. And really the only thing I'm missing from my Kf expression is the copper, which is what I'm looking for. So what I'm going to do now is basically take, just like normal, my equilibrium line and put it into my equilibrium expression. And if I do that, I will end up with 0.2 up on top divided by the copper concentration, which is what I'm looking for. My 0.4, which I still need to do what with it? I still need to take it to the fourth power. Yeah, so you don't want to forget that. You still need to do that. And that's going to equal my Kf value here, 5 times 10 to the 13. We're now going to solve for copper, which if you multiply the copper to the other side and then divide the Kf back, what ends up happening is these two guys switch places, basically. Yeah? So you're going to multiply the copper 2 to the other side, divide by the 5.0 times 10 to the 13, and you will end up with the copper concentration will equal squeaky feet 0.2 divided by 5 times 10 to the 13. And we have our 0.4, still remembering to take it to the fourth. So now we put that into our handy dandy calculator we got somewhere. We do that little dividing there. Don't do what I just did and make it negative 13. It's actually positive 13. So 0.2 divided by 5 to the positive 13 divided by 0.4 to the fourth. Gonna give us I'll go over here. Gonna give us a copper concentration of 1.6 times 10 to the minus 13 molar in this case. Yeah. First off, any questions on that there? Did our second assumption come true? Is the amount of copper a lot or very, very small? It is super small. Pretty much nothing's there, right? You got to go out like 12 decimal places to find some copper hanging out there freely. So pretty much our first assumption is correct, right? In this example, pretty much all of it, all that copper ends up in the complex ion. There's still a smidge of free copper two floating around, and it should be very small. So when you're asked these type of questions, which is a very common question that's asked, is how much of that free metals is floating around. If you end up with a really large value for your free metal, you definitely did something wrong. So it should really be a small number, and that's a good way to check yourself. You didn't make any type of math. This also demonstrates something we'll talk about as well, that definitely the formation of a complex ion is super favored, right? Because pretty much you get a really good ligand next to a metal, they're just going to come together and make that complex ion, as we can see with the really large value of Kf. Any questions on that one there? All right, let's take a look at another problem here. That's the same problem. Let's take a look at a different one. All right, here. Calculate the concentration of everybody in a solution that's prepared by mixing 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. We actually are given down here the stepwise formation of the complex ion. So take a few moments here, may want to add those together, get an overall reaction, and kind of work it from there. So in this case, we're looking for everybody's concentration. Here, we're not keeping anybody's volumes constant, so you got to take that into account as well to get the proper concentrations. So work on that for a few, and then we'll talk. Okay, let's take a look, see how you're doing. So, like I said before, in this particular problem, as I mentioned earlier, sometimes you are given more of a stepwise formation of that complex ion. So, probably a good approach on this deal is to maybe get the overall reaction. So, once again, we can get the overall reaction really just by adding these together to two steps. We will see that this guy will sort of cancel out. And that will leave us our overall reaction of silver plus two of our ligands in this case. Will give us our complex ion here. And obviously we could get a Kf for our complex ion. Again, remember that we multiply the K values here, not atoms. So that's going to get us here, looks like a 7.4 to the 8 times 3.9 to the fourth. Call it a 2.9 times 10 to the 13. Any questions so far on that? So we can really, since we're looking for like everybody's concentration, we can use the overall reaction here to sort of get some concentrations. Before we do that, we do want the concentration of everybody in that overall reaction after they're kind of mixed together. So we do have to do a little M1V1 equals M2V2 action. So here the silver nitrate is going to be our source of silver in this case. So the concentration of silver in this case would equal our 1, looks like, times 10 to the minus 3 molar times the volume there, which is 150 milliliters we're going to use of it. And now obviously here we want to divide by our total volume, which is 150 and through 200. That's going to give us 350 milliliters of our total volume. When we do that, milliliters will cancel. And that's going to give us a silver concentration here of, I don't know, we'll go with 4.29 times 10 to the minus 4. We'll do the same thing for our ligand right here. This is going to be the source of our ligand. So the concentration of our S2O32 minus. Again, we have a concentration of 5 molar of it. We're using 200 milliliters. And again, when we mix it all together, we're going to have 350 milliliters here. And we will end up with 5 times 200 divided by 350. 2.86 molar here. Any questions on that one there? Now that we have really our mixed concentrations, we can again really use our overall reaction here and start getting some of these answers that we're looking for, since we're looking for a bunch of different things, obviously, in here. So let's do that. I'm just going to rewrite the equation over here. So we have our silver plus our couple of these guys going to our complex ion here. All right, so initially on the previous slide there, we saw our silver concentration 4.29 times 10 to the minus 4, 2.86 there for our S2O3 from the previous calculation right there, and 0 here. So once again, as we could also see from our Kf value that we calculated, it is again a large value, which typically our Kf values are. So once again here, we're going to make the assumption that all the silver should get tied up into that complex ion. So again here, we don't use X's, but we actually use numbers, and it is going to be the metal as the change part here. So we'll go with minus my metal here, 4.29 times 10 to the minus 4. Minus, remember, we also got to do like a 2x here, right? So this is going to be 2 times 4.29 times 10 to the minus 4. And this will be plus 4.29 times 10 to the minus 4. That means at equilibrium here, we're going to end up with 0 of that guy. We'll go 2.86 minus 2 times 4.29 to the minus 4. Basically still 2.86, 2.859, pretty close, and 4.29 times 10 to the minus, bless you, minus 4. Now, at the end of this particular ice table, we actually have a couple of answers that we could use. We obviously know that the concentration of S2O32 minus, which I'm not sure was actually asked for, is 2.86 molar, right? We also can see that the concentration of our complex ion here at equilibrium, 4.29 times 10 to the minus 4. So we got this guy here. And that's going to be our 4.29 times 10 to the minus 4 molar. So we got this guy done. We have our complex ion. Now, at this point, you do have a couple of options as to where you want to go after next. So I'll show it maybe both options here. I'm going to choose at this point to decide to go for this guy's concentration next. And the reason I'm going to choose to do that is I actually have the stepwise formation here that we did earlier. And off of my first ice table I just did, I now have this guy's concentration. I have this guy's concentration. And that using the second step there will allow me to find that sort of intermediate concentration from that. So I could kind of use the second step there because it's an equilibrium and actually figure out that guy's concentration. And then my thought process here is after I do that, I will then have that guy's concentration and that guy's concentration, and then I could get myself over to silver if I want to at that point. So that's sort of the process here. I'm going to choose to do so. So I am going to use the K2 expression down here to do that. And that means if I write my K2 equilibrium expression, it is the concentration of my complex ion divided by my concentration of that sort of intermediate guy that I'm looking for, and my ligand there. And that's going to equal my K2 value there that was on the previous page and on the bottom, 3.9 times 10 to the fourth. Now, the question people always ask at this point is, don't you need to square this guy? Why am I not squaring that guy? Yeah, because I'm not using the overall reaction here, right? And if I were using the overall reaction, I should be using the KF value I calculated, but I'm not. I'm using specifically the second step where clearly the coefficient here is 1. Yeah. So here I would not square it because again, I'm using that equilibrium reaction to figure out what I need. So now at this point, we can pop in some numbers that we have from the table. Maybe I'll just go this way with it. We'll go 4.29 times 10 to the minus 4 is my equilibrium. I'm looking for this guy's concentration still. And my ligand is 2.86. Just like the math on the last one, these two guys are basically just going to switch places. When you do it, you're going to multiply the bottom guy to the other side and divide by the K value. And that will get you that this sort of intermediate guy, which was asked for in the question, will end up with 4.29 times 10 to the minus 4 divided by this guy swapping in its place, 3.9 times 10 to the 4, and our 2.86. And that's going to get us here. Minus 4 divided by 3.9 exponent, but then there we go. And divided by 2.86. And that's going to give you a lot of zeros with a 4 at the end. Or if you're in scientific notation, you'll get something maybe like 3.8 times 10 to the minus 9. Or again, if you're not in scientific notation, you have a bunch of zeros with that 4 probably at the end of your calculator. And that's perfectly fine as well. Any questions on that there? As I mentioned a second ago, now that I have that guy's concentration, I will obviously have this guy's concentration. I still have this guy's concentration. I could actually still use just the stepwise equations to figure out the silver concentration. And now I'm going to go to K1 here and use that equation because those are all equilibrium concentrations. Those are all equilibrium reactions. And now I'm going to use K1 to figure out the silver concentration, which will be my little intermediate guy I just calculated. And my silver concentration. And again, my ligand as well. And again, that's going to equal our K1 value, 7.4 to the 8. Once again, here I am not squaring the ligand because I am using this equation where it's just 1 is the coefficient. So put it in our numbers there. We're going to take our 3.8 times 10 to the minus 9 divided by our silver, our 2.86 equals 7.4 times 10 to the 8. Once again, here we're going to swap spots right there. That's going to yield me a silver concentration of 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8 and 2.86. By the way, based on our assumption, our silver concentration should be a large number or a small number. Should be a small number. Let's see if we get a small number here. I hope so. Otherwise, I'm out of room on the paper. And we end up with a free silver concentration of 1.8 times 10 to the minus 18, which I would say classifies as a small value of free silver that's floating around in that solution. First off, any questions on that part? As I mentioned earlier, there are different approaches that you could take at this point. Here, I just wanted to demonstrate that you could go to each of the individual steps, and because there are equilibrium reactions and you have equilibrium concentrations, you could just kind of plug and chug into there and get what you needed. You could absolutely, if you wanted to, go after the silver concentration first, like we did previously. So if you were to do that, you would take the KF value that we calculated right earlier, which was 2.9 times 10 to the 13. So that was KF 2.9 times 10 to the 13. And you would take your overall reaction and you could write your equilibrium expression for that, which would be our KF is equal to our silver, two of those, divided by our silver concentration. Whoops, I'll need a +1 there. And our S2032 minus. And here I would square it because now I am using the overall reaction here, right? So here I do need to square it because I am using that overall reaction. Now we could put in our numbers just like before. We would get 2.9 times 10 to the 13 equals and from that first ice table, we had 4.29 times 10 to the minus 4 for that guy. Divided by the silver concentration. And for this guy, again, from that first ice table, the combined ice table there, we had 2.86. And here we would square it. Once again, we're going to swap spots there. And we would end up with this. And if we put that in there, we should get the same number. Otherwise, just ignore everything I just said. Let's see how we did here. 2.86. I hope we'll just add that little disclaimer in there as well. And looky, it is a 1.8 times 10 to the minus 18 molar. So obviously you could have done very much like we did on the first problem. You could have went right after the silver concentration using the same assumption. Obviously, going to get tied up. Now we could go back and solve for how much is actually there. Yes. We did. We used it up here. In terms of well, we found the initial concentration. So what we found, which was the 4.29 times 10 to minus 4, that's kind of your true initial concentration of silver that went in there. Remember, once it goes in, it's going to start reacting. And after it starts reacting, what we're left with is what we have at the end of this ice table. So remember, like when we put it all together, technically speaking, there's like a second, or however you want to think about it, right? Before things start reacting, that's kind of like what you put in there. Yeah, it's what you put in there initially is the 4.29 times 10 to minus 4. But technically, once you do that, it's going to go find the ligand and they're going to start reacting, right? So that's kind of like your initial concentration of what you supplied as silver in there. And then the 2.86 is initially technically the concentration when everybody's mixed together, initially what you supplied into that beaker. Now they're going to start reacting and their concentration is going to come down. And because of the KF, the assumption is all that metal is just going to keep going and reacting until pretty much it all gets used up. And when it's all technically done and reaches equilibrium, right, which is what happens at the end there, once everybody's done reacting, now the rates of the forward and reverse directions equal each other, it's going to pretty much zero out the metal that's there. But even though we kind of zeroed it out mathematically in our calculation, because it is still kind of going back and forth, like you said there at the end there, there's just going to be a little bit of it that is going to go in the other direction. And you will technically end up with a little bit of that free metal floating around, and it should be a really small number. Yeah. You can if you're asking in this type of problem, you can use the individual ones like I did the first time to solve it here, and you get obviously as you can see the same answer. You can definitely take the different approach of I want to go with the metal first, like I did this way, and get the same answer, right? And at this point, though, you would be forced at this point to has to go back to one of those equations to find the middle guy, because this little intermediate guy that the question asks you for is not in the overall reaction. So at that particular point, if you did this sort of, you went with the silver first, you actually have to now go back into either one of those at this point. You would have the option of either one and go back and figure out what the concentration of that like intermediate is. So you would have to kind of use those kind of intermediate steps or the stepwise to figure out that guy. It's kind of similar if you remember when we did the like phosphoric acid example, that titration problem, and it wanted the concentration like phosphate, right? And because it wanted the concentration of phosphate, we had to go all the way down to like the third reaction, right? Because that's the only place where phosphates is. So it's kind of a similar idea. If this is the question, which is what was asked here, at this point, you would definitely have to go into one of those to figure out that intermediate. Other questions? All right, fun times. Maybe not. I don't know. All right. Now we want to know the important question of if you did those qualitative analysis experiments, you actually do this actual question right here. We want to calculate what is the molar solubility of silver chloride in 1 molar ammonia. So why don't we talk about it here together and see what we end up with. So we are given in this problem here two different types of equilibrium. We have our favorite KSP that we talked about earlier on in this chapter. So we have our silver chloride going to our silver ion plus our chloride ion. And that's going to make 1.6 times 10 to the minus 10 as the KSP. We have then the formation of a complex ion, which is the silver and the ammonia coming together to make our silver and ammonia complex ion, which later on you'll know how to name that properly. A little diamine, silver 1 ion going on there. And that's a KF there. So we can, since we have two equations here, we could always add them together because that's fun, right? So we can do that. And dare I say, in this case, my silver actually goes away. And I end up with a silver chloride plus a couple of ammonias. Uh, Give me my complex ion and some chloride. By the way, is it okay I added these together since one's a KSP and one's a KF? Is that okay? I hope so because I just did it. So I'm hoping that I did. And it can. It doesn't really matter, right? They're all essentially, no matter what the little guy on the bottom says, right? KC, KP. I'm trying to remember all the ones we did. KW, right? A nice flashback here, right? We had our KSP or KF. I feel like I'm missing a bunch of them. KA, KB, all those guys. They're all really just equilibrium constants, right? So they're all the same thing. So it doesn't really matter. You can add them together. That also means I have no problem multiplying both of those guys together, right? So it's no different than when you did KW equals KA times KB, right? So same idea. So to get the K value for this sort of combined equation, I could take these two guys and multiply them together, and I will get a 1.6 to the minus 10 times a 1.5 to the 7 in this case. That's going to give me a K value here of 2.4 times 10 to the minus 3. All right, so when we read the problem, we are looking for the molar solubility of silver chloride in ammonia, and that's good because in my overall reaction, I have silver chloride reacting with ammonia, so that's kind of what I'm looking for in this case. By the way, because we're looking for the molar solubility, do you think this is going to be more of a KSP problem or a KF problem? This is going to be more of a KSP problem, right? So this is more like a solubility problem. As you can also see when we look at the combined K value, we don't really have a giant K value like we do with KF, right? We now have a kind of a smaller one there, a minus 3, more like a KSP type of a K value. So that's what we're going to do. So we're going to take my combined equation here. Oh, that's nice. I have the equation right there again. So we got our silver chloride plus our cup of ammonias going to my complex ion and my chloride in this case. Again, we got the K value there, which is to the minus 3, I think 2.4 times 10 to the minus 3. All right, so in this particular case, the only thing that's really given to us in this problem is you got 1 molar of ammonia. So that seems like a good place to start. We'll put 1 molar ammonia here. The rest are going to be zeros. Now, a little different in this sort of combo reaction. We normally in a KSP don't do anything on the left-hand side, but we do have ammonia that's aqueous, so we do need to do something with it. So we're going to go with a minus 2s here, and this is going to be a plus s and a plus s, right? Since we are looking for the molar solubility, we'll use S instead of X to represent that. That's going to give us a 1 minus 2S, an S, and an S. Any questions on the ice table here? Once again, although we are kind of interested in silver chloride's solubility, it is a solid, so we're not going to put any numbers or anything in it in the table. This is going to go into our K expression, which for our combined reaction will be our complex ion times our chloride divided by our ammonia. And once again, we do need to square it because of the coefficient here. So popping in our numbers here, that's going to give us an S times an S divided by a 1 minus a 2S squared is equal to 2.4 times 10 to the minus 3. Well, being professionals we are, I see a big square root. I hope you do too. Yes. So we can big square root both sides there. And that's going to reduce this down to S divided by 1 minus 2S there. I lost my 2 there. 2S. There you go. Is equal to, I probably should square root the other side so I don't make any more mistakes. Let's see, 2.4 to the minus 3 there. That's going to get us a 4 point, I call it 9 times 10 to the minus 2. We're going to multiply this to the other side. That's going to get us an S is equal to 4.90 times 10 to the minus 2 minus, looks like 9.8 times 10 to the minus 2S. Going to add that back to the other side, right? And if I do that, we're going to do that plus a 1 here. That's going to get me a, looks like 1.098 S is equal to 4.9 times 10 to the minus 2. Obviously, at this point, we're going to divide that to that side. And that's going to go 4.9 to the minus 2 divided by that answer. Going to get us a molar solubility here of 4.5 times 10 to the minus 2 molar, right? And if we wanted it in grams per liter like we did earlier, we will end up with, what number go there? 4.51. There it is. About 6 point, we'll call it 4 grams per liter is silver chloride's molar solubility in ammonia. First off, any question on that? Now, oh, yeah, say one more time. I did, yeah. So kind of like we did before. So remember, I'll put it right here. So 4.5 times 10 to the minus 2, that's moles per liter. And we'll times it by, I think it was 143.35 grams per mole is the molar mass of silver chloride. Yeah. And that gets us that answer. Now, if you remember, we did the molar solubility and solubility of silver chloride in water earlier. And just to remind you of that, that was this calculation, right? Which was our silver plus our chloride and our KSP 1.6 to the minus 10. And if you remember, we basically would go 0, 0 plus S, and get just S and S. S squared equals 1.6 times 10 to the minus 10. S on the square root there. Just to refresh our memory of what we got there earlier in water was 0.0000126 moles per liter times 143.35 grams per mole. Got us 0.0018 grams per liter. That is the solubility of silver chloride in water. Which one is more? That is 6 grams you could get to dissolve in 1,000 milliliters of water. You get 0.002 grams in regular water to dissolve, right? Way more soluble in the ammonia. That also reinforces what we talked about earlier, that because these KF values are so large, the formation of a complex ion is actually super favored, if it's possible, than anything else. This is so favored that, as I was describing earlier, that qualitative analysis experiment where you had a solid of silver chloride sitting there, the solid, that is why when you have the silver tied up in a solid and you take something like ammonia, which is actually the test there, and you toss it in there, because of the formation of complex ion is so favored, it is able to remove that silver from that solid and make this complex ion. And that's how favored it is, right? Usually you can't get something out of the solid really easily. You add some ammonia, the ammonia is there, and the silver goes, I'd rather hook up with the ammonia, a much better deal for me. And it will take it out of the solid as well. That's also why, just so you know, as I mentioned earlier, the final test for this is you hit it with nitric acid. And because you hit it with nitric acid, that makes it too acidic for that to stay together. And now you free up the silver ion, And as you can see in this problem, it is no problem for that free silver now to find the chloride. And now, because it's no longer basic and that ammonia is gone, the solid will come back together because it's going to go, yeah, now you're my best option at this point. All the ammonia is left. Your best option now is I'm going to hook up now with the chloride and make that solid. So that is why what we see with our KF values, if they're really large, it definitely indicates that it is definitely a favored situation. If you have a good ligand, you got a nice metal, they're going to want to definitely come together to make that complex ion. And again, as you can see in that sort of calculation, almost a ton more could get dissolved in ammonia than you could in just water. Any questions on KF? KSP, KF, oh my. Yes. That is the end of chapter 15 and the end of exam 2 material.